In 1933, an astronomer named Fritz Zwicky noticed something impossible. The galaxies in the Coma cluster were moving too fast, far too fast. By all the physics anyone knew, they should have been flying apart. There was not enough visible mass to hold them together. So Zwicky proposed that there must be invisible mass, matter we cannot see, matter that does not emit light, does not absorb light, does not interact with anything we can measure. He called it dunkle materie, dark matter. And for 90 years, that invisible substance has been the foundation of modern cosmology. It is supposed to make up 27% of the entire universe. We have built our models of galaxy formation on it. We have based our understanding of how the cosmos evolved on it. We have run some of the most expensive experiments in the history of science to detect it. And we have found nothing. Not one particle, not one signal. 90 years, billions of dollars, zero detections. In April of 2026, a major scientific paper proposed something that would have ended careers to suggest a decade ago. Dark matter probably does not exist. And if that is true, everything we thought we knew about the structure of the universe needs to be rebuilt from scratch. Why dark matter was invented. Let me take you back to the beginning. 1933. Fritz Zwicky, a Swiss astronomer working at Caltech, is studying the Coma cluster, a massive collection of galaxies about 321 million light-years from Earth. He measures the velocities of the galaxies within the cluster. Then he calculates how much mass the cluster needs to hold itself together gravitationally. The numbers do not match. The visible mass, all the stars, all the gas, everything he can see and measure, accounts for only about 1% of what the gravitational math requires. 99% of the needed mass is missing. Zwicky's conclusion: there must be invisible mass, dark matter. The idea sat quietly for decades. Then in the 1970s, astronomer Vera Rubin made the same discovery in a different context. She was measuring the rotation curves of individual galaxies, how fast stars at different distances from the galactic center rotate around it. According to Newtonian gravity, stars further from the center should move slower, like the outer planets of our solar system move slower than the inner ones. They do not. Stars at the edges of galaxies rotate at almost the same speed as stars near the center. The rotation curves are flat, and they stay flat. This is only possible if there is far more mass than we can see, a massive invisible halo of dark matter surrounding each galaxy, providing extra gravitational pull to the outer stars. The theory fit the observations perfectly. Dark matter became the accepted explanation. And here is the critical thing to understand. From 1933 to today, dark matter has always been theoretical. It was invented to explain observations that could not otherwise be accounted for. No one has ever detected it directly. That has always been the understanding. The plan was always, we predict it must exist, so we find it. For 90 years, we have not found it. 90 years of failed detection. Let's talk about what 90 years of looking like. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, spanning 17 miles underground, costing over $4 billion, was expected to produce dark matter particles in its collisions. It has been running since 2008. 0 dark matter particles detected. The Lux Zeppelin detector, buried 1.5 kilometers underground in an old gold mine in South Dakota, surrounded by 70,000 gallons of water shielding, operating at a temperature colder than outer space, specifically built to detect dark matter particles passing through the Earth. 0 detections. The Exinen 1 experiment at Gran Sasso in Italy. 0 detections. Pandex in China. 0 detections. The Fermi Gamma Ray Space Telescope, searching for gamma ray signatures that dark matter annihilation should produce. No clear signal. The Alpha Magnetic Spectrometer aboard the International Space Station. No unambiguous dark matter signal. These are not small experiments. These are the largest, most sensitive, most expensive physics instruments ever built. They have been looking for different types of dark matter candidates, WIMPs, axions, sterile neutrinos, using completely different detection methods. All of them have found nothing. And here is the thing that keeps physicists awake at night. Each time a detector found nothing, the scientific community said, it must be that the dark matter particle is lighter than we thought, or heavier, or interacts more weakly. We adjusted the theory to explain the null result, and then built a more sensitive detector, which also found nothing. At some point, and many physicists argue we reached that point years ago, the repeated failure to detect something is itself evidence.
evidence that it may not be there. The 2026 study, Everything Changes. In April 2026, a study published in a major peer-reviewed journal proposed something that the mainstream scientific community has been slow to accept for decades. The researchers analyzed galaxy formation data using new high-precision measurements from the James Webb Space Telescope, the most powerful space telescope ever launched, which has been returning data since 2022. What they found was unexpected. Galaxies were forming in the early universe, appearing in the data, far earlier than the standard cosmological model predicted. The standard model, called lambda CDM, which stands for lambda cold dark matter, makes specific predictions about when and how galaxies should form, predictions that depend heavily on dark matter providing the initial gravitational scaffolding around which ordinary matter collapses. The James Webb data showed galaxies that are too large, too early, too structured, too early, more evolved, more complex, too early. The early universe, according to the Webb data, looks nothing like what lambda CDM predicts. The 2026 study proposed two things. First, the universe may be significantly older than the current estimate of 13.8 billion years. Some calculations put it closer to 26 billion years. This would give galaxies more time to form without requiring dark matter scaffolding. Second, the cosmological model itself, the lambda CDM framework built on dark matter, may need fundamental revision. Not tweaking, not adjusting parameters. Rebuilding. This is not a fringe paper. It draws on James Webb Telescope observations that are verifiable, reproducible, and that multiple independent research teams have now confirmed. The galaxies are there. They should not be there according to our model, and the simplest explanation is not we need more dark matter. The simplest explanation is that the model is wrong. What Mond theory proposes instead? If dark matter does not exist, what explains the galaxy rotation curves that Vera Rubin discovered? There is a competing theory that has been around since 1983. It is called MOND, Modified Newtonian Dynamics. Proposed by Israeli physicist Mordecai Milgram, MOND says the problem is not missing mass. The problem is that our equations for gravity are slightly wrong at very low accelerations. Newton's law of gravity works perfectly in the solar system, where gravitational accelerations are relatively strong. But at the extremely low accelerations experienced by stars at the edges of galaxies, Milgram proposed that gravity behaves differently. Slightly stronger than Newton's equations predict. Just enough to explain the flat rotation curves without needing any invisible matter at all. MOND has been controversial for 4 decades. The mainstream cosmological community largely rejected it, because while it explained galaxy rotation curves well, it struggled with other things, like the behavior of galaxy clusters, that dark matter explained more easily. But in recent years, something has shifted. Every new galaxy that the James Webb Telescope discovers, including the unexpectedly early, unexpectedly massive ones, fits MOND's predictions more accurately than lambda CDM's predictions. Not as an accident, consistently. A team at Case Western Reserve University published a paper showing that MOND correctly predicted the properties of over 150 galaxies that lambda CDM failed to predict. This does not prove MOND is right, but it suggests that modifying gravity, rather than adding invisible matter, may be closer to the truth. And if gravity is slightly different at very low accelerations, the implications go far beyond galaxy rotation curves. It means every calculation in cosmology that assumed standard Newtonian gravity at all scales needs to be revisited. Every single one. If dark matter does not exist, what does it exist? Let's think about what it would actually mean if dark matter does not exist. First, 27% of the universe, the amount that dark matter is supposed to account for, is simply gone from the accounting. Our current model says the universe is roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. If dark matter does not exist, we have directly accounted for 5% of the universe. 95% is unknown. This is actually already the honest statement of where we are, but it would become impossible to avoid. Second, every simulation of galaxy formation that cosmologists run uses dark matter. Every model of cosmic evolution, every prediction about how large-scale structure forms, the cosmic web of galaxy filaments and voids that spans the observable universe. All of it is built on dark matter scaffolding. Without it, every simulation needs to be rerun, every model needs to be rebuilt. Decades of computational work. Third, the detection programs, LHC, Lux Zeppelin, Exanen, Pandex, would represent the most expensive series of null results in the history of science. Not failures of the experiments worked perfectly. Failures of the theory that motivated them. And fourth, the most philosophically uncomfortable consequence. If we got dark matter wrong, what else are we wrong about? If a concept that has been the consensus view of physics for 90 years can turn out to be undetectable and potentially non-existent, what else in our model of the universe is a placeholder for something we simply do not understand yet? What this means for the universe we thought we knew. I want to be precise about what is happening here, and what is not. This is not a settled debate. Dark matter remains the consensus view among most cosmologists. The lambda CDM model, despite its problems with the James Webb data, has explained too many observations too successfully to be simply discarded. What is happening is something more nuanced, and actually more interesting. The James Webb Space Telescope has given us data that the standard model was not designed to produce. The early universe looks different from what we expected. That discrepancy is real. It is confirmed by multiple teams. It is not going away. The debate is now about interpretation. One interpretation: dark matter exists but behaves differently than our models assume. The models need refinement. Another interpretation: dark matter does not exist. Gravity is modified at low accelerations, and the universe is older than we calculated. The framework needs replacement. A third, more unsettling interpretation: we are missing something entirely, a piece of physics that neither dark matter theory nor MOND correctly captures. Something new, something we have not imagined yet. Each of these interpretations has serious physicists arguing for it. None of them have been proven. What the James